December 19th, 2025. Everyone's watching the sky, counting down to a cosmic near miss that won't even come close. But while you're staring at Earth, something far stranger is unfolding. 3I Atlas isn't slowing down. It's accelerating toward Jupiter, and the math suggests something nobody wants to say out loud. What if this isn't about dodging a bullet? What if we're watching the setup for something exponentially worse? A gas giant with the chemistry of a star, waiting for ignition. A binary system that could rewrite physics as we know it. Stay with me until the end, because what happens next at Jupiter makes December 19th look like a practice run, and the clock is already ticking. Stay with us, because 3I Atlas is still revealing its secrets in real time. Observatories are tracking whether its approach to Jupiter triggers new anomalies or shatters our current models entirely. Hit subscribe to follow this unfolding mystery, because what happens over the next months might force us to completely rethink what interstellar objects are capable of. Now, let's settle in and explore this cosmic puzzle together. You've seen the headlines. December 19th, 2025. A date circled in red across forums, whispered in comment sections, trending under apocalyptic hashtags. An interstellar visitor named 3I Atlas hurtles toward us through the cosmic dark, and the internet has decided this is it. The end. The moment when humanity's number finally gets called. But here's the thing, nobody's telling you. The thing buried beneath the panic and the clickbait and the survivalist prep videos. December 19th isn't the end of anything. It's barely even the middle. Because while everyone's staring at Earth, counting down the hours until this cosmic stranger arrives, they're missing the actual story. They're looking at the wrong target entirely. Let me give you the numbers first, the cold scientific truth that should calm your racing heart, but probably won't. On December 19th, 3I Atlas will pass approximately 1.8 astronomical units from Earth. That's roughly 170 million miles. To put that in perspective, an astronomical unit is the distance between Earth and the Sun, about 93 million miles of empty space. This thing is passing at nearly twice that distance, twice the gulf that separates us from our own star. The moon sits 239,000 miles away. We've walked there. We've planted flags and driven rovers and left footprints that'll outlast empires. That distance feels conquerable, almost intimate. But 170 million miles? That's not a near miss. That's not even in the same category as a near miss. That's the universe, giving Earth the widest possible berth, while still technically being in the same solar neighborhood. NASA confirmed it. European Space Agency confirmed it. Every major observatory with the equipment too. Track this object has confirmed it. The trajectory is hyperbolic, meaning 3I Atlas isn't sticking around. It's not slowing down to take up residence in our solar system. It's moving on a curved path that'll whip it through our cosmic backyard and sling it right back out into the interstellar medium from which it came. No capture, no collision, no last-minute swerve toward our fragile blue marble. So why the panic? Why are people stockpiling food and posting tearful goodbye videos and treating December 19th like some kind of cosmic judgment day? Because fear fills the gaps that knowledge leaves empty. Because 170 million miles sounds both impossibly far and terrifyingly close, depending on how the headline phrases it. Because we're pattern-seeking creatures living in a universe that doesn't care about our patterns. And when something unfamiliar enters our awareness, we default to the dramatic. We write the disaster movie in our heads before the scientists can finish writing their observations. The memes don't help. You've seen them. The memes claiming 3I Atlas adjusted its course. The threads insisting that official sources are lying, that the real distance is classified, that world governments know something we don't. But here's the reality check. If this thing were actually on a collision course with Earth, you wouldn't hear about it from a guy with 17 followers posting blurry charts at 3 in the morning. You'd hear it from every government simultaneously because they'd have no choice. You can't hide an extinction-level impact. Too many telescopes, too many observers, too many amateur astronomers with equipment good enough to track objects across millions of miles. The observatories tracking 3I Atlas aren't seeing any deviations. The path remains consistent. The math checks out. December 19th will come and go, and Earth will still be here, spinning through space exactly as it was on December 18th. But here's where the story gets interesting. Here's where we stop talking about what won't happen and start asking the question that should have been asked from the beginning. If 3I Atlas isn't coming for Earth, if it's passing us by with room to spare, then why are scientists watching it so closely? Why the coordinated observation campaigns? Why the careful tracking and the spectrographic analysis and the urgency in the academic papers? Because Earth was never the destination. We were just a landmark along the way. A signpost this thing passes on its journey to somewhere far more consequential. 3I Atlas is headed for Jupiter, and that changes everything. Not immediately. Not on December 19th when the comet makes its harmless flyby and the doomsayers quietly delete their predictions. But later. March 16th, 2026. That's when the real show begins. That's when this interstellar traveler reaches the king of planets, the gas giant that dominates our solar system with a mass greater than all other planets combined. 0.358 astronomical units. That's how close 3I Atlas will come to Jupiter. Still millions of kilometers of separation. Still no collision, no impact, nothing that would make for good disaster footage, but close enough to interact with Jupiter's immense gravitational field. Close enough to be studied in ways we've never studied an interstellar object before. Close enough, some say, for something else entirely. I need you to stay with me here, because this is where the science splits from the speculation, where the observable universe bumps up against the fevered imagination of conspiracy theorists who've watched too many science fiction films. I'm going to show you both sides. I'm going to give you the facts, and then I'm going to show you what people are building on top of those facts, the towers of conjecture rising from foundations of truth. But first, you need to understand something about Jupiter. Something that'll matter later when we dive into the really wild theories. Jupiter is a failed star. That's not hyperbole or metaphor. Jupiter has the same basic composition as the Sun, mostly hydrogen and helium, the fuel that powers stellar fusion. But it lacks the mass to ignite that fuel. Jupiter would need to be about 75 times more massive to achieve the temperatures and pressures necessary for hydrogen fusion. It's not even close. It's a cosmic near miss, a stellar wannabe that never quite made it to the big leagues, which makes it, according to some, the perfect candidate for artificial ignition, the perfect target for something or someone who wants to create a second sun. Does that sound insane? Good. Hold on to that feeling. We're going to need it for what comes next. March 16th, 2026. Mark that date. While everyone else is recovering from the non-event of December 19th, while the debunkers are taking their victory laps and the fearmongers are quietly pivoting to new apocalypses, 3I Atlas will be making its real approach, not to Earth, to Jupiter, and the distance, 0.358 astronomical units, translates to roughly 53 million kilometers. Still vast, still safe, still nowhere near collision territory. But let me tell you what that distance isn't. It isn't random. It isn't accidental. It's a consequence of trajectory and velocity and the gravitational choreography that governs how objects move through space. 3I Atlas entered our solar system on a specific path, influenced by the sun's gravity, following the mathematics that Johannes Kepler worked out 400 years ago. The fact that it passes near Jupiter isn't mysterious. Jupiter's gravitational well is so immense that anything passing through the outer solar system has to account for it, has to bend its path around that massive presence. The phrase direct intercept course gets thrown around in the comments, in the videos, in the breathless speculation pieces. It sounds ominous. It sounds intentional. But here's what it actually means. Nothing. The comet is following the path that physics dictates based on its entry velocity and angle. If you fire a bullet past a magnet, the bullet's path curves. That doesn't mean the bullet chose to approach the magnet. That doesn't mean someone programmed the bullet to target the magnet. It means magnetic fields affect metal objects. Gravity affects everything. Jupiter appears in these narratives not because the comet is aiming for it, but because Jupiter is impossible to ignore. It's 11 times wider than Earth. Its mass is 318 times greater than our planet's. Its gravitational influence extends so far that it shapes the orbits of comets in the outer solar system, sweeps debris from the inner solar system, and serves as a cosmic shield protecting Earth from impacts we'll never know we avoided. So when something from interstellar space enters our neighborhood, of course, Jupiter factors into the trajectory. Of course, the path bends toward the gas giant. Physics doesn't care about narrative tension. But physics also doesn't stop people from asking, what if? What if Jupiter could be ignited? What if those layers of hydrogen and helium, the same elements that fuel the sun, could be triggered into fusion? What if 75 solar masses isn't a hard requirement, but a natural threshold, one that could be bypassed with the right technology, the right catalyst, the right push from something we don't yet understand? This is the Lucifer Project scenario, named, somewhat unfortunately, after a work of science fiction. The idea that Jupiter could be transformed from a planet into a star, that our solar system could shift from a single star system to a binary configuration, that the night sky could suddenly acquire a second source of light and heat. Let me be absolutely clear. No credible scientific institution supports this. None. The physics are prohibitive. The energy requirements are staggering. Jupiter isn't just slightly too small to be a star. It's catastrophically too small. The core temperature of Jupiter is around 20,000 Kelvin. The core temperature needed to sustain hydrogen fusion is around 10 million Kelvin. That's not a gap you bridge with a match and some optimism. That's a fundamental difference in the type of object we're discussing. Brown dwarfs, the smallest objects that can sustain deuterium fusion, require at least 13 Jupiter masses. Even they don't achieve full hydrogen fusion like our sun does. They're cosmic in-betweens, too big to be planets, too small to be stars, glowing faintly in infrared while failing to ignite the reactions that make stars shine. To turn Jupiter into a star, you'd need to add mass. Lots of mass. More mass than exists in all the other planets, moons, asteroids, and comets in our solar system combined. You'd need to fundamentally restructure the object's composition and density. You'd need to compress it beyond anything natural forces could achieve. Or, and this is where the speculation takes flight, you'd need technology so advanced it makes our current understanding of physics look like cave paintings. The conspiracy theorists love this angle. They love the hidden agenda narrative, the idea that powerful forces know more than they're telling. They love pointing to Jupiter's composition and saying, look, the ingredients are there. All we need is ignition. They love invoking Arthur C. Clarke's sufficiently advanced technology is indistinguishable from magic, and using it as a blanket justification for anything they can imagine. And honestly, I understand the appeal. Mystery is intoxicating. The possibility that we're not seeing the full picture, that somewhere in the classified briefings and the redacted reports, there's knowledge that would rewrite everything we think we know about our place in the universe. That's compelling. That scratches an itch that mundane explanations can't quite reach. But wanting something to be true doesn't make it true. And the absence of proof isn't proof of absence. but it's also not permission to believe whatever fills the void most dramatically. The real science here is actually fascinating enough without the fiction. The fact that spacecraft like Juno are currently orbiting Jupiter, studying its atmosphere and magnetic field and internal structure. The fact that the JUICE mission, the Jupiter Icy Moons Explorer, will arrive at the Jovian system in 2031 to study Europa, Ganymede, and Callisto. The fact that when 3I Atlas passes by in March of 2026, we'll have the opportunity to observe an interstellar object interacting with a gas giant's environment in ways we've never seen before. We could learn about the comet's composition by watching how Jupiter's radiation belts interact with its coma. We could refine our models of how interstellar objects behave when subjected to intense gravitational forces. We could gather data that helps us understand planetary formation, not just in our solar system, but in others across the galaxy. That's the real opportunity here. Not ignition, not binary stars, not a second sun rising over Earth's horizon. Just science, just the slow accumulation of knowledge that lets us build better models and ask better questions. But I promised you I'd show you both sides. So let's acknowledge what makes people nervous. Let's look at what 3I Atlas is actually doing as it approaches. What's been observed, what's been measured, what doesn't quite fit the comfortable categories we've built for comets and asteroids and space debris. Because something is definitely odd about this thing. And odd is where speculation takes root. The images started coming back in October. High-resolution observations from observatories across Earth, multiple instruments trained on this visitor as it rounded the sun and began its outbound journey. What they showed was simultaneously exactly what you'd expect from a comet, and completely unlike anything we've seen before. The coma, that cloud of gas and dust that surrounds a comet's nucleus when solar radiation heats its surface, was developing normally, or mostly normally. The structure was there, the expected brightening, as 3I Atlas approached perihelion, the closest point to the sun in its trajectory. But the details, the fine structure within that coma, those raised questions. Color changes for one thing. Observers noted shifts in the comet's appearance, a greenish tint that intensified as it warmed. This isn't unprecedented. Comets often glow green due to the presence of diatomic carbon, a molecule that forms when sunlight breaks down larger organic compounds on the comet's surface. The carbon molecules absorb solar radiation and re-emit it at specific wavelengths, creating that eerie green luminescence you see in long exposure photographs. So the green is explainable. The green is chemistry. The green is what happens when frozen compounds from interstellar space meet the sun's heat and start to sublimate, turning from solid to gas without passing through liquid phase. But the intensity of that green, the specific wavelengths being emitted, those suggested something unusual about 3I Atlas's composition. More organic compounds than expected, perhaps. A different ratio of carbon-based molecules. A chemistry that formed in conditions unlike those that created comets born in our solar system. Then there's the X-ray emission. Comets emit X-rays when solar wind particles interact with gases in the coma. It's a well-documented phenomenon. But the X-ray signature from 3I Atlas was stronger than models predicted. Not massively stronger. Not in a way that breaks physics. Just enough to make scientists take note and wonder what about this object's composition or structure was amplifying the effect. Organic compounds showed up in spectroscopic analysis. Life-building molecules. The amino acids and carbon chains that could, under the right conditions, with enough time and the right environment, assemble into something more complex. Finding these in comets isn't shocking. We've known for years that comets likely delivered some of the organic material that contributed to life's emergence on Earth. But every new data point refines that understanding, helps us build a more complete picture of how chemistry distributed itself across the galaxy. What caught attention, what generated whispers in the observation community, was the abundance and variety. 3I Atlas seemed to be carrying a richer cargo of organic complexity than previous interstellar visitors. Enough to make astrobiologists excited. Enough to fuel speculation about where this thing formed. What kind of stellar neighborhood could produce such chemistry? Then there are the acceleration anomalies. Small ones. Tiny deviations from the predicted path that could be explained by outgassing, by jets of material erupting from the nucleus as sunlight heats different regions. Comets do this all the time. They're not solid chunks of rock. They're more like dirty snowballs, frozen volatiles mixed with dust and larger fragments, all held together by weak gravity. When they warm up, they don't warm evenly. One side faces the sun, gets hot, starts venting material. That venting creates thrust. Tiny thrust, but enough to alter the trajectory slightly. So when 3I Atlas showed non-gravitational acceleration, the first response was outgassing, case closed. But some observers noted timing irregularities. Perihelion occurred roughly when predicted, but some community posts suggested it might have been earlier or later than initial calculations indicated. Refinements in measurement, perhaps, errors in early trajectory estimates, or actual deviations that require explaining. The problem is separating signal from noise. When you're tracking an object hundreds of millions of miles away, when you're measuring velocities and positions down to tiny fractions, when you're accounting for gravitational influences from multiple planetary bodies, errors accumulate. Small uncertainties in initial measurements propagate through your calculations. What looks like an anomaly might just be the limit of measurement precision. But what if it's not? What if those tiny deviations represent something real? Something that standard comet behavior doesn't quite capture? The tail structure added another layer of strangeness. Most comets have two tails, a dust tail pushed by solar radiation pressure, and an ion tail pushed by the solar wind. Sometimes you see an anti-tail, an optical illusion created when Earth's viewing angle makes it look like material is streaming toward the sun instead of away from it. 3I Atlas displayed all of these, but the anti-tail persisted longer than expected. The geometry required to produce that effect should have changed as the comet moved, but observers kept reporting the phenomenon well past the point where viewing angle alone could explain it. Jets of material erupting from specific locations on the nucleus were visible in high-resolution images. Again, not unusual for comets. But the patterns were asymmetric in ways that suggested either a very irregular nucleus shape or localized regions of unusual composition. Something about the surface wasn't uniform. Something was venting more vigorously from certain areas than others. None of this, and I want to be absolutely clear about this, none of this proves anything exotic. Comet Hale-Bopp in 1997 displayed unusual outgassing patterns. Comet Hartley 2 showed jets coming from specific locations. Comet 67P, visited by the Rosetta spacecraft, had an incredibly irregular duck-shaped nucleus with localized active regions. Comets are weird. They're ancient, frozen relics from the formation of planetary systems. They've spent billions of years in deep space, subjected to cosmic radiation, occasional collisions, gravitational perturbations. They're not uniform spheres. They're not predictable. They're lumpy, irregular, chemically diverse objects that do strange things when you heat them up. But 3I Atlas is different in one crucial way. It didn't form here. It formed somewhere else, around some other star, in a protoplanetary disk with different chemistry, different temperatures, different starting conditions. So when it does something unusual, we can't just compare it to solar system comets and say, close enough. We have to wonder if what we're seeing is just normal interstellar comet behavior, or if we're glimpsing something genuinely new. And that's where the uncertainty lives. That's the gap between what we know and what we're guessing. That's the space that speculation fills with increasingly wild hypotheses. Some of those hypotheses are scientific, refined models of comet formation in different stellar environments. Questions about how long 3I Atlas traveled through interstellar space before arriving here, and what that journey might have done to its structure. Theories about exotic ice compositions that could explain the unusual outgassing patterns. But some of those hypotheses go further. Some ask whether what we're calling a comet might be something else entirely. Something shaped, something artificial. Something that's not just passing through our solar system, but carrying out a mission we can't yet comprehend. Is there any evidence for that? Any actual data that supports the idea of 3I Atlas being something other than a natural object? Not really, but the absence of evidence creates a vacuum, and nature famously abhors a vacuum. So does human curiosity. So let's stop pretending we're above the speculation and dive directly into it. Let's ask the uncomfortable question that nobody in the scientific establishment wants to touch. What if 3I Atlas isn't just a comet? We need to establish some ground rules before we go any further. We need to understand the difference between observation, hypothesis, and conjecture, because we're about to cross some lines that make scientists uncomfortable and conspiracy theorists giddy. Observation is what we measure. The greenish glow, the X-ray emissions, the trajectory, the organic compounds. These are facts. We saw them. Multiple independent observers confirmed them. The data exists. Hypothesis is what we propose to explain those observations. Outgassing explains acceleration. Diatomic carbon explains the green color. Solar-wind interaction explains the X-rays. These are testable proposals that make predictions we can verify. Conjecture is what we imagine beyond the data. The stories we tell when observations don't quite fit our existing hypotheses, or when the implications of accepting the mainstream explanation feel somehow insufficient. Conjecture is where we entertain possibilities that lack supporting evidence but can't be definitively ruled out. We're about to enter conjecture territory, and I want you to know that going in, the techno-object hypothesis is the big one, the idea that generates the most heat in online discussions. It goes something like this. 3I Atlas displays behaviors that, while not impossible for a natural comet, are statistically unusual. The trajectory seems almost precisely calculated to pass Jupiter at a specific distance. The timing of its arrival in our solar system, just as our observation capabilities reach the point where we can study such objects in detail, feels convenient. The organic complexity, the unusual outgassing, the X-ray emissions, all of these could be side effects of technology we don't recognize as technology because we're looking for the wrong signatures. Avi Loeb floated similar ideas about Oumuamua back in 2017. He suggested that its unusual acceleration and elongated shape might indicate an artificial origin, perhaps a light sail or probe from another civilization. The scientific community largely rejected that interpretation, proposing natural explanations involving unusual outgassing or exotic ice compositions. But Loeb's speculation opened a door that's hard to close. It normalized asking whether interstellar objects might be something other than rocks and ice. 3I Atlas reignited that debate. Online communities analyzed the trajectory, looking for signs of deliberate maneuvering. Some claimed they found slight adjustments inconsistent with pure gravitational motion. Mainstream astronomers explained these as measurement uncertainties or natural non-gravitational forces. The debate continues. The issue is that proving something is artificial is incredibly difficult when you can't get close to it, when all you have are distant observations and indirect measurements. You're looking for anomalies in a dataset full of noise. You're trying to distinguish deliberate from accidental in a universe where accidental produces some very odd outcomes. So what would artificial look like? What signatures would we expect from a probe or vessel traveling between stars? Honestly, we don't know. We've never seen one. We're making assumptions based on how we'd build such a thing, but our technology is laughably primitive compared to what would be required for interstellar travel. Maybe advanced civilizations don't use propulsion we'd recognize. Maybe they coat their vessels in ice and dust to protect from interstellar radiation, making them look like comets. Maybe the energy signatures we'd look for are deliberately masked. Or maybe we're overthinking it. Maybe 3I Atlas is exactly what it appears to be, a chunk of frozen material ejected from another star system, traveling for millions of years through empty space before coincidentally passing through ours. The universe is big. Objects get ejected from stellar systems all the time. Some of them are bound to wander past Earth eventually. But let's push the speculation further. Let's ask about the mass and acceleration debate. Some fringe analyses suggested that 3I Atlas's mass, calculated from its brightness and assumed composition, doesn't quite match the acceleration observed. If it's lighter than expected, outgassing could produce the observed thrust. If it's heavier, you need more force to explain the deviation. Natural explanations exist. Maybe the composition is different than we assume, affecting both the mass calculation and the outgassing efficiency. Maybe the nucleus is porous, reducing density. Maybe there are subsurface voids or unusual structural features. Comets are diverse. We've visited only a handful of them directly. Assuming we know what typical looks like is premature. But the speculation asks, what if the mass discrepancy is real and significant? What if something about this object's structure doesn't fit natural formation scenarios? What then? Then we'd need to seriously consider alternatives. And that's where things get wild. JWST data hinted at unusual coma composition. Carbon dioxide ice, which sublimates at different temperatures than water ice, appeared more abundant than in solar system comets. This could indicate formation near a CO2 ice line in another protoplanetary disk. Different stars have different temperature gradients in their planet-forming regions. If 3I Atlas formed in a system with a cooler or hotter star than our Sun, its chemistry would reflect that environment. So, we're learning something about planetary formation in other systems. We're seeing the products of stellar neighborhoods with different conditions. That's scientifically valuable. That's exciting, even if it's entirely natural. But it also raises questions. If this object formed in radically different conditions, if its composition is optimized for some environment unlike what we see in our solar system, does that tell us something about where it came from? Could we trace it back to a specific type of star, a specific stellar age, a specific region of the galaxy? The interstellar precedents complicate the picture. Oumuamua was small, elongated, tumbling weirdly, accelerating in ways that sparked debate. Borisov looked more like a standard comet, with a familiar coma and tail structure, less controversial. 3I Atlas falls somewhere between. Familiar enough to be recognized as cometary, strange enough to generate questions. What we didn't know about Oumuamua, we're learning now. What we didn't measure in time, we're measuring with 3I Atlas. Each visitor refines our understanding and reveals new mysteries. Some researchers have even suggested these objects could help test physics at the edges of our understanding. Dark matter interactions, modified gravity theories, exotic particles that only reveal themselves in interstellar space. These are long shots, ideas that most physicists would dismiss, but they're not completely impossible. Science advances by testing unlikely ideas and seeing which ones survive scrutiny. The problem is knowing when to stop speculating and start testing. Speculation without testability is just storytelling. And while storytelling has value, while it generates hypotheses and keeps people engaged, it can't substitute for actual evidence. So where does that leave us? With observations that are interesting but not revolutionary. With hypotheses that explain most of what we see. With conjecture that fills gaps but lacks proof. With an interstellar visitor that's probably exactly what it seems to be, but maybe, possibly, could be something more. Science will test these ideas. Observations will continue past December 19th and through the Jupiter flyby. Data will accumulate. Models will be refined, and eventually we'll know more than we do now. Not everything. Probably not enough to satisfy everyone, but more. And if 3i Atlas really is artificial, if it really is carrying out some mission we can't fathom, then the data will eventually reveal that. Evidence doesn't hide forever. Patterns emerge. Anomalies accumulate until they can't be explained away. Until then, we watch, we measure, we wonder. We hold space for both the probable and the possible, knowing that the universe has surprised us before and will certainly surprise us again. 2017 changed everything. Before Oumuamua, interstellar objects were theoretical. We knew they had to exist. The mathematics of stellar formation demanded it. When star systems coalesce from clouds of gas and dust, when planets form and migrate, material gets ejected. Gravitational interactions fling asteroids and comets out of their home systems at velocities high enough to escape the star's pull entirely. That material wanders. It travels between stars, through the vast emptiness that separates stellar neighborhoods. We knew this happened. We just hadn't seen it yet. Our detection capabilities weren't good enough. The sky is big. Interstellar objects are small and dark and move quickly. Finding them requires the right combination of telescope sensitivity, survey coverage, and timing. Oumuamua was discovered on October 19th, 2017, by the Pan-STARRS telescope in Hawaii. The name means scout, or first distant messenger in Hawaiian. Appropriate, given that it was our first confirmed visitor from beyond the solar system. It was small, roughly 400 meters long, tumbling end over end as it raced through the inner solar system at nearly 90,000 kilometers per hour. What made Oumuamua controversial was its behavior. It accelerated as it moved away from the sun, a non-gravitational effect that comets display when outgassing creates thrust. But Oumuamua showed no visible coma, no tail, no obvious signs of material venting from its surface. So where was the thrust coming from? Various explanations were proposed. Maybe it was outgassing hydrogen, which is nearly invisible to our instruments. Maybe it had a strange shape that created asymmetric thermal effects. Maybe it was partially coated in organic material that sublimated without producing a visible coma. Or maybe, as Avi Loeb suggested, it was artificial. A light sail, a piece of technology, something deliberately sent to study other star systems. The scientific community largely settled on natural explanations, but the debate revealed something important. We don't actually know what interstellar objects should look like. We don't have a large sample size. We're making assumptions based on solar system comets and asteroids, but objects that formed elsewhere, that spent millions of years in interstellar space exposed to cosmic radiation, might behave differently. Borisov came next. Discovered on August 30th, 2019, by amateur astronomer Gennady Borisov, this object was more cooperative. It looked like a comet. It had a coma and tail. It outgassed in predictable ways. Its composition seemed familiar, though spectroscopic analysis revealed some differences from solar system comets. More carbon monoxide, different isotope ratios, clues about its formation environment. Borisov was less controversial, but more scientifically valuable in some ways. It confirmed that interstellar comets exist and that they can resemble objects from our own solar system. It gave researchers a chance to study composition and structure in detail. It provided a comparison point for future discoveries. Now we have 3i Atlas, third confirmed interstellar visitor. Discovered earlier in its approach than the previous two, giving scientists more time to prepare observations. More complex than Borisov, less controversial than Oumuamua, strange enough to generate questions, but familiar enough to study using existing techniques. The detection technologies improved between each discovery. Pan-STARRS improved. The Vera Rubin Observatory, scheduled to begin operations soon, will detect interstellar objects at an unprecedented rate. Within a few years, these visitors will shift from rare anomalies to regular occurrences. We'll have enough samples to understand what's typical and what's unusual. What previous visitors taught us is humility. They taught us that our solar system isn't the only template for how planetary systems work. They taught us that the space between stars isn't empty, but filled with wandering material. Refugees from distant stellar neighborhoods carrying information about conditions we can't observe directly. The trajectories tell us about galactic dynamics. Objects don't just get ejected randomly. They follow paths determined by their home system's structure and the gravitational influence of nearby stars. By tracking these trajectories back, by calculating their likely origins, we can map regions of the galaxy we'll never visit directly. The speeds tell us about escape velocities and stellar masses. Fast-moving objects came from more massive systems. Slower objects might have originated closer or been ejected more gently. Each velocity is a data point constraining models of stellar evolution and planetary formation. Hyperbolic trajectories mark interstellar origin definitively. Objects born in our solar system move on elliptical paths, bound to the sun's gravity, returning again and again, even if their orbits are thousands of years long. Hyperbolic paths are open-ended. The object passes through once and never returns. It's just visiting, not staying. 3i Atlas follows a hyperbolic trajectory. It came from somewhere else, and it's leaving, headed back to the interstellar medium with no intention of becoming a permanent solar system resident. Solar system science benefits enormously from these visitors. Every interstellar object is a natural experiment, a test case for theories of planet formation. We can compare compositions, structures, behaviors. We can see what changed during billions of years in interstellar space versus billions of years orbiting the sun. Cosmic radiation affects surfaces differently than solar wind. Temperature regimes differ. Collision rates vary. By studying these differences, we refine models. We learn which formation processes are universal and which are specific to our solar neighborhood. We build better predictions for what we'll find when we finally start studying exoplanets directly, when our instruments get good enough to analyze the atmospheres and surfaces of worlds orbiting other stars. The public fascination follows predictable patterns. When Oumuamua was discovered, social media erupted with speculation. Alien probe, ancient spacecraft, deliberate visitor. The science got lost in the noise. Researchers tried explaining the observations, but explanations are boring compared to possibilities. It's probably just a weirdly shaped comet. Doesn't generate clicks like, could this be alien technology? The same pattern repeated with 3i Atlas. Early observations generated excitement. Unusual features sparked speculation. The speculation built on itself, becoming more elaborate and disconnected from evidence. Scientists tried to correct the record, but corrections don't spread as fast as sensational claims. This matters for planetary defense. We need to know what's out there. We need to detect incoming objects early, determine their trajectories, assess whether they pose threats. Most objects don't. Most pass harmlessly. But someday, something won't. Someday, we'll detect an object on an actual collision course, and we'll need to respond. The technologies we develop to study interstellar visitors directly serve planetary defense. Better detection systems, faster trajectory calculations, more accurate composition models, the ability to distinguish natural from artificial, outgassing from deliberate maneuvering, genuine threats from harmless flybys. We're building that capability now, one visitor at a time, one observation at a time, one refinement to our models at a time. It's slow. It's painstaking. It's the opposite of the instant gratification our media-saturated culture craves. But it's how science works. Accumulation of knowledge, testing of hypotheses, gradual improvement in understanding, not dramatic, not cinematic, but effective. And when the genuine crisis comes, If it comes, we'll be ready because of this slow preparation. 3i Atlas is part of that preparation. It's teaching us. And we're learning, even if what we're learning isn't the story the headlines want to tell. December 19th will pass. The countdown clocks will hit 0. The doomsday predictions will fail to materialize. Earth will continue spinning. The sun will rise on December 20th, exactly as it rose on December 18th. Life will continue, indifferent to the panic that preceded it. And 3i Atlas will keep moving. It won't stop. It won't linger. It'll follow its hyperbolic path deeper into the solar system, heading outward from the sun, carrying its cargo of frozen volatiles and organic molecules and whatever mysteries its composition holds. March 16th, 2026. That's the next milestone. That's when this visitor reaches Jupiter's orbital neighborhood, passing within 0.358 astronomical units of the gas giant. 53 million kilometers of separation. Close in astronomical terms, meaningless in collision terms. No impact, no gravitational capture. Just a flyby, though one that offers unprecedented scientific opportunities. Jupiter is surrounded by an intense radiation environment. Charged particles, trapped in its powerful magnetic field, create radiation belts that would fry unshielded electronics. These particles interact with anything passing through them, exciting molecules, creating auroras, generating X-rays, and radio emissions. When 3i Atlas passes through this environment, we'll be watching. Multiple instruments will observe how the comet's coma responds to Jupiter's radiation, how the solar wind, already weakening at Jupiter's distance from the sun, interacts with the comet's outgassing, how Jupiter's gravity affects the trajectory and potentially the comet's rotation and internal structure. Juno, NASA's spacecraft currently orbiting Jupiter, might be positioned to observe. Its instruments weren't designed to study comets, but they can detect changes in the local radiation environment, magnetic field perturbations, anything the comet's passage triggers. The data might be indirect, but indirect data still teaches us things. JUICE, the Jupiter Icy Moons Explorer launched by the European Space Agency, won't arrive at Jupiter until 2031. It'll miss the 3i Atlas flyby entirely. But the lessons learned from observing this encounter will inform JUICE's mission planning. Understanding how interstellar objects behave near gas giants helps researchers design better observation strategies for future encounters. Ground-based telescopes will track 3i Atlas throughout its approach to and departure from Jupiter. Multiple wavelengths, multiple instruments, coordinated campaigns involving observatories around the world. The goal is comprehensive coverage, minimal gaps in the data, the kind of detailed monitoring that lets you catch unexpected phenomena if they occur. Space-based telescopes add capabilities that ground instruments can't match. Hubble might observe if its schedule permits. The James Webb Space Telescope, with its infrared sensitivity, could study the comet's thermal emissions and composition in unprecedented detail. These are valuable resources with many competing demands, but an interstellar object passing Jupiter is the kind of event that justifies telescope time. The scientific questions researchers hope to answer are specific and technical. How does the comet's outgassing change in response to Jupiter's magnetosphere? Does the radiation environment alter surface chemistry in detectable ways? Can we measure the nucleus's rotation and shape more precisely using the Jupiter encounter as a gravitational probe? Does the trajectory bend exactly as Newtonian mechanics predicts? Or are there tiny deviations that might indicate internal structure or composition surprises? These questions won't generate headlines. They're not dramatic. They're the kind of detailed work that builds understanding incrementally, one measurement at a time. But they're important. Every data point constrains models. Every observation tests theories. Every answer generates new questions. The comet's exit from the solar system is inevitable. After Jupiter, 3i Atlas will continue outward, crossing the orbits of Saturn, Uranus, Neptune. Its velocity, already high, won't be enough to escape the sun's gravity immediately, but the hyperbolic trajectory guarantees eventual departure. Decades from now, it'll cross the heliopause, the boundary where the solar wind yields to the interstellar medium. It'll return to the space between stars, carrying whatever information it gathered during its brief passage through our neighborhood. By then, it'll be too faint to observe, too distant, too small. Our instruments will lose track of it. It'll become one more object in the census of things we detected briefly and then lost. Its data will remain, archived in databases, available for future analysis as our understanding improves. But the object itself will be gone. What unresolved questions will remain? Probably many. We might never know exactly where 3I Atlas originated. We might never pin down its age or the conditions under which it formed. We might never fully explain all the unusual observations, all the small anomalies that don't quite fit standard models. That's normal in science. Complete understanding is rare. We work with probabilities and confidence intervals and best available explanations. We accept uncertainty while pushing to reduce it. We acknowledge what we don't know while celebrating what we've learned. But surprises remain possible. Comets have surprised us before. Sudden brightness changes. Unexpected fragmentation. Outbursts that weren't predicted. 3I Atlas could still do something strange. It could split as it swings past Jupiter, revealing internal structure we couldn't see before. It could brighten or dim unexpectedly. It could display new features in its coma or tail. Scientists are ready for surprises. That's part of the excitement. The known is valuable, but the unknown is where discoveries live, where new physics might be hiding, where our models might break down and reveal their limitations. So December 19th isn't an ending. It's barely even a milestone. It's a date that will pass quietly, while everyone who panicked about it, quietly, pretends they never believed the hype. The real story continues. The real observations come later. The real science happens after the headlines move on to the next apocalypse that isn't coming. And if you're paying attention, if you're following the actual data instead of the fear-mongering, you'll see something remarkable. Not an alien invasion. Not a second sun. Not the end of the world. Just a visitor from beyond, passing through our cosmic neighborhood on its way to somewhere else, teaching us what we're willing to learn. That's the story. Not the one you've been told, but the real one. The one worth your attention. 3I Atlas will leave. That's certain. Objects on hyperbolic trajectories don't stick around. They pass through, and they exit, following mathematical laws that don't care about our desire to study them longer, to squeeze more data from their composition, to answer every question their presence raises. But what they leave behind matters. Not just data, though the data is valuable. Not just refined models and better understanding of cometary physics. They leave something more fundamental, something that shapes how we think about our place in the universe. They prove we're not isolated. Our solar system isn't a closed bubble, separate from the galaxy. Material flows in. Material flows out. We're part of a larger system, connected to stellar neighborhoods we'll never visit, sharing chemistry with star systems billions of years old and light years away. Every interstellar visitor is a message, not in the sense of deliberate communication, though that possibility can't be entirely dismissed. A message in the sense of information, chemical signatures, structural features, trajectories that encode details about formation conditions and stellar environments and the processes that govern matter's behavior across cosmic scales. We're learning to read these messages, slowly, imperfectly, with gaps in our understanding that might never completely close. But we're learning. We're getting better at distinguishing interstellar from solar system origin, better at calculating trajectories and predicting encounters, better at planning observations that capture the most scientifically valuable data. The contrast between actual science and sensational hype reveals something about human psychology. We want drama. We want significance. We want to believe we're living through unique moments, witnessing events that will be remembered centuries from now. A harmless comet passing at a safe distance doesn't satisfy that desire. So, we invent threats. We imagine conspiracies. We turn natural phenomena into apocalyptic scenarios. This tendency isn't new. Every comet bright enough to see with naked eyes has inspired fear. Every astronomical event we couldn't immediately explain has generated wild theories. Halley's Comet in 1910 was supposed to poison Earth's atmosphere with its tail. Didn't happen. Comet Hale-Bopp in 1997 was supposedly followed by an alien spacecraft. Wasn't. The pattern repeats because the psychology remains constant. But here's what's interesting. The fear serves a function. It generates attention. People who would never voluntarily read about orbital mechanics or spectroscopic analysis will click on an article promising apocalyptic revelations. They'll watch videos explaining trajectories if those videos are framed as uncovering hidden threats. The sensationalism brings audiences who might otherwise ignore science entirely. The challenge is converting that attention into understanding, meeting people where they are, acknowledging their concerns, then gently guiding them toward actual knowledge. Not talking down, not dismissing their questions as stupid, but showing them that reality, properly understood, is more interesting than fiction. Scientific humility requires acknowledging how much we don't know. We've studied 3 interstellar objects. 3. That's not enough to make sweeping generalizations about what's typical or what's unusual. We're still in the early stages of understanding this class of objects. Our models will improve. Our predictions will become more accurate. But right now, we're learning the basics. That's exciting, not limiting. Being at the beginning of understanding means discoveries are more likely. Every observation could reveal something unexpected. Every measurement could challenge existing theories. The unknowns outnumber the knowns, and that's the perfect environment for scientific progress. The future of interstellar object studies is bright. The Vera Rubin Observatory, once fully operational, will detect dozens or hundreds of these visitors. We'll have enough examples to perform statistical analysis, to categorize, to understand which features are common and which are rare, to trace probable origins and predict future encounters. Spectroscopic techniques will improve. We'll learn to extract more information from the light these objects emit or reflect. We'll identify specific molecules, measure isotope ratios with greater precision, characterize surface properties, and internal structures. Each technological advance expands what's knowable. Mission concepts exist for intercepting interstellar objects. Spacecraft that could launch quickly when an object is detected, accelerate to rendezvous velocities, approach close enough for detailed study. These missions are technically challenging and expensive, but they're possible. Someday, probably within the next few decades, we'll send a probe to study an interstellar visitor up close. We'll see the nucleus directly. We'll sample the coma. We'll gather data that remote observation can never provide. Cultural and philosophical implications ripple outward from these discoveries. Every interstellar object reminds us that Earth isn't the center of anything. We're not special. We're not unique. We're one planet among billions, in a solar system among hundreds of billions, in a galaxy that's one of trillions. Matter moves between these systems. Chemistry distributes itself across cosmic scales. The processes that built our world operated elsewhere, are operating elsewhere now, will continue long after our civilization ends. That perspective can be humbling or liberating depending on how you frame it. Humbling because it reminds us how small we are, how insignificant our individual concerns seem against the backdrop of cosmic time and space. Liberating because it suggests possibilities beyond our immediate experience, connections to phenomena we're just beginning to comprehend. 3i Atlas is a traveler. It formed somewhere we can only guess at, around a star we can't identify, in a planetary system that might no longer exist. It wandered for millions or billions of years, surviving collisions and radiation exposure and the absolute cold of interstellar space. It entered our solar system by chance, following a trajectory determined by gravitational interactions we can calculate but not control. It's passing through. It's leaving. It won't return. But for a brief moment, we shared space with it. We pointed our instruments at it. We measured its properties. We wondered about its origin. We speculated about what it might mean. We learned from it, even as we acknowledged how much we still don't understand. That's the real story of 3i Atlas. Not the panic, not the conspiracies, not the false threats and manufactured drama. The real story is simpler and more profound. We detected something from beyond our solar system. We studied it to the best of our ability, and we expanded our understanding of the universe we inhabit. That's science. That's discovery. That's the slow, incremental progress that builds knowledge across generations. And as 3i Atlas slips back into the darkness between stars, as it becomes too distant for our instruments to track, as it disappears from our awareness entirely, it leaves behind one undeniable truth. We are not alone in the universe, not in the sense of encountering alien intelligence, though that possibility remains open. Alone in the sense that our solar system is connected to the galaxy, that material flows between stars, that the chemistry of our world has siblings in distant stellar neighborhoods. That connection matters. It shapes how we understand ourselves and our place in the cosmos. It transforms Earth from an isolated oasis into a node in a galactic network, a participant in processes larger than we can fully comprehend. 3i Atlas proved that again. A visitor from elsewhere, carrying messages we're learning to read, teaching us lessons we're beginning to understand. Not threatening, not ominous, just there, passing through, reminding us that the universe is bigger and stranger and more connected than our daily experiences suggest. That's the real revelation, and it's more than enough.